Hello, doctor. My name is Tan Chunming. So now I'm going to talk about the first question in part C for the left 5. So from the first question, we can see that the instruction given is move AL with this binary bit, which and we need to end AL here, and we have the another binary bit here. So from here, we can compare whether it is true or false for each bit. So from the if we see from the left to the right, so the first one will be 0 0, which is 0. The second one is 1 0, which is also 0 because of the AND gate. The third one is 1 0, same is 0. The fourth one is 0 1, is also 0. The fifth one is also 0 1, which is also 0. The sixth one is also 0 1, which is also 0. The seventh one is 0 0, which is absolutely 0. And the last one will be 1 1, which is true. So we have one bit right here. So if we change from the binary bit to the hexadecimal, so we'll also get one. The value of the AL is also 1. So move to the second instruction. So it asks us to move AL from 12 hexadecimal, and we need to use the AND gate, and we need to compare with the 3B hexadecimal. So from here, I already changed the basis for both of the value, which is 12 and 3B, and this is the binary value for the 12 hexadecimal, and this is the binary value for the 3B. So if we compare here, we can find out that from the left to the right, we have the fourth bit, which is true, and also with the 7 bit, so true, it's also true from if we count from the left to the right. So we will so if we transpose the answer, which is 1 0 0 0 1 0, we will get 12 in the in hexadecimal. Then move to the next one. We have the instruction move AL with this binary bit, which is 0 0 0 0 1 1 1 1, and we will use the OR gate, and we'll compare with the 72 hexadecimal. So this is the binary value for the 72 hexadecimal, and if we use the OR gate, so for the OR gate, we know that if one of the value is 1, and another one maybe is either 0 or 1, as long as there's one side of the value is 1, then the value will be true. So from here, we will find out that every bit except the MSB will be 1 because of it contains at least one in the comparison right here. So if we transpose this, we change the basis to hexadecimal to 16, so we will get 7F right here for this instruction. And the last one is the instruction will be move AL with 83 hexadecimal, and we use the XOR gate, which is we will compare with 26 hexadecimal. So I already transpose change the base for both of the value. So if we compare for the XOR gate, we know that the value will be 1 if the value contain one of the one inside the comparison. So it will also be 0 if we have both 1 1 or 0 0. So in this case, we will have 1 0 1 0 0 1 0 1. So if we change the bases into the 16 to 16, so we will get a 5 for the value of AL. So that's it for the first question. Hello, doctor. My name is Tan Ming. So now I'm going to talk about the question 2 for lab 5. So the second question asks us to write instructions in assembly language code that so the first question is jumps to label L1 if either bit 4, 5, or 6 is set in the BL register. So from here you can see I use test BL and I set the 4th, 5, and 6 bit right here, and I will jump to loop 1 if gen z, which is jump if not equal to 0. So in this case, the instruction will jump to 0. Will jump to loop L1, which hits the requirement of the question. So the second one, it asks us to jump to label L1 if bits 4, 5, and 6 are all set in the BL register. So in here, you can see I use N BL, and I assign this binary bit right here, and I compare with another binary bit, and the jump if jump the instruction will jump if this both of this value is equal, because I use the JE here, which means that jump is equal, and it will jump to L1. So the next question is jumps to label L2 if AL has even parity. So I use OR gate to declare whether AL and compare with AL. So I use the JP, which is the JP, which is the jump if parity, which is even. So in this case, it will jump because I use the same value right here. So it will jump to L2. So the next question, it will jump to label 3 if the EAX is negative. So I will compare the EAX with 0. So I use the JL, which is the jump if less, which is less than 0. If it's less than 0, then it will jump to the L3. And then the last one is jumps to label L4 if I think this is if the expression is EBX minus ECX is greater than 0. So firstly, I will subtract the EBX with the ECX right here, and I'll compare it. I'll compare the EBX whether it's whether it's greater than 0 or not. If it is greater than 0, which is I use JG right here, which stands for jump if above, then it will jump to L4. So this is for the question 2. Thank you. Hello, doctor. So I'm going to talk about the question 3. So we are given some the code segment right here, and I need to answer two questions right here. So the first question is if the EX is equal to 25, so which conditional jump is taken, and I need to explain my answer, and I also need to tell what is the final value of the EBX. So from here, we know that firstly, our EAX will be 25. So back to the code, we'll find out that we need to compare the EAX with 20. So we know that 25 is greater than 20. So in this case, we will jump if above will be taken. Conditional jump if above will taken, which is will enter the loop 1 right here. I mean L1 right here. So in the L1, we know that we will move the 1 into the VX. So, and we will jump to the out, which is right here, which is have nothing right here. So our final value of the EBX will be 1. And for the second question, why is the jump out, which is this line, jump out, instruction is needed for this code segment, and I need to elaborate my answer. So this is because why we need this instruction is because if we don't have this instruction, then we will, after the L1, we will directly move into the L2. So if we don't have this this instruction, our the final value of the EBX will be 0. Then these two conditional jump has doesn't affect a lot if once our EX is greater than 20. So this code, this line is important because that we don't want to change our. We need to maintain our value of EBX, which is 1 here, until the end. If our value of the EX is greater than 20. So we can find out that we just add the instruction right here, but not in the L2, because if it is less than 20, then it will directly enter the L2, which won't execute back to the L1. So this is the reason why the jump out, which is this line instruction, is needed for this code segment. So that's it for the question 3. Hello, doctor. So I'm going to talk about the left 5, question 4. So from here, we can find out that we are going to use 3 kinds of loop. From here, we need to write these three instruction right here. So I'm going to show in my Visual Studio 2019. So for the first one, which is using loop. So firstly, I move the move 0 into the EAX, and I'll enter L1. So inside the L1, I will add EX with the ECX. And I'll loop the L1, and I'll return the value back to the main code here, which is right here. Okay, so for the second one, we will enter the using decrement and jump not equal. So firstly, same, I'll move 0 into the EAX, and I'll enter the L1. So from here, I'll add the EAX with the ECX, and I'll use the decrement. I'll use the decrement ECX, which is the counter right here, and I will compare the ECX with 0, and if it's not equal to 0, then it will jump back into this L1. And after, if it's equal to 0, so this line will not be executed, so it will directly return to the main code right here. So the third one is using decrement, jump if the ECX is equal to 0, and it will jump. So firstly, the same, I move 0 into the EAX, and inside the, I have two label right here, which is L1 and L2. So inside the L1, I add the ECX into the EAX, and same, I will do the decrement for the ECX. So I have two conditions right here. So if the ECX is equal to 0, so it will jump into the L2, which is returned back to the main code. And if it's not equal to 0, so this line will not be executed, so it will directly jump to this, will go to this line, and from this line it will execute, which is jump to L1, so it will jump back to here, which is the L1, and it will execute again as like a loop, so until the ECX is equal to 0. So let us try to run here. So I use an example of 5. So we can see that 1 plus 2 plus 3 plus 4 plus 5, which is equal to 15. We have the same value for 3 of the function or loop, we can say. So this for this millisecond is because that we can see from here. So from here, we have so that's all for the question 4. So that's all for the question 4, lab 5.